A very good afternoon, Professor Mohammed, and good evening to all participants and my colleagues. It's a great pleasure to introduce you to our guest of today and speaker, distinguished speaker, Professor Mohamed-Slim Alouini, who is a fellow IEEE and also IEEE Communication Society distinguished lecturer. He is from King Abdullah University of Science and Technology, Kingdom of Saudi Arabia. Professor Mohammed was born in Tunis, Tunisia. He received his Ph.D. degree in electrical engineering from the California Institute of Technology, Caltech, Pasadena, California, US, in 1998. He served as a faculty member at the University of Minnesota, Minneapolis, US, and then in Texas A&M University at Qatar, Education City, Doha, Qatar, before joining the King Abdullah University of Science and Technology, KAUST, Thuwal, Saudi Arabia, as a professor of electrical engineering in 2009. His current research interests include the modeling, design, and performance analysis of wireless communication systems. He has published several papers on the above subjects, and he is co-author of a textbook, Digital Communication Over Fading Channels, published by Wiley Inter-science. He has been honored in 2007 with the Organization of Islamic Cooperation, Science and Technology Achievement Award in Engineering Science at the first OIC Summit on Science and Technology, Astana, Kazakhstan. Prior to this, he received the 2016 Recognition Award of the IEEE Communication Society Wireless Technical Committee and 2016 Abdul Hamid Soman Award for Arab researchers in engineering sciences. Other recognitions include his selection as Fellow of Institution of Electrical and Electronics Engineers, IEEE, the African Academy of Science, AAS, the European Academy of Science and Arts, ESA, SA, and Academia Europea, AE. IEEE Distinguished Lecturer for the IEEE Communication Society and IEEE Vehicular Technology Society. He is a member for several times in the annual Thomson ISI Web of Knowledge list of highly cited researchers, as well as the Sanghal ranking Elsevier list of most cited researchers. He is a co-recipient of Best Paper Award in 11 IEEE conferences, including the reputed ICC, Globecom, VTC, PIMRC, ISWCS, and DY-SPAN. We are very much fortunate today that Professor Mohammed has kindly agreed to deliver a talk on our very latest topic, what should 6G be? I thank you, Professor Mohammed, for accepting our invitation. Professor Mohammed, you can start your lecture now, sir. Thank you.
Thank you very much, Professor Das, for the nice introduction. I'm somehow trying to share my screen, but I'm not able to see the screen I would like to share on the other side. I'm not sure why. Maybe I should disconnect and reconnect. Should I do that? Because I'm not able to see, when I try to share my screen, I'm not able to see the PDF file. Maybe I should disconnect and reconnect, okay?
Okay, it's fine.
Okay. Do you see my screen, Professor Das, now?
Perfect, sir. Perfect, sir. Please continue, sir.
Very good. Thank you very much for, again, the nice introduction. Thank you for the invitation to share with you some of our thoughts on basically what should the 6G be. Let me remove the camera so that we focus on the slide. I will put the camera on again during the Q&A session. And let me put the full screen here so that hopefully it's very clear from the other side. Okay. So, I think the best way to start this talk is to talk about the mobile revolution that we have been witnessing over the last 4 or 5 decades. It's kind of this nice merger between the internet, electronics, wireless communication that kind of led to this very nice evolution of wireless communication. It's kind of mind-boggling that now we are able to use our phone for so many functions and so many services that have been viewed in the past as kind of independent functions. And the thing is that as users, we are still not fully satisfied. We would like always to get better services, better performance, better connectivity, more coverage, lower latency, and so on and so forth. And obviously, this is not new thing. We have seen this kind of movie over and over again over the 4 or 5 previous decades. So if you remember, the 80s was in a way the proof of concept stage. That was the time when we have kind of seen the first generation of wireless communication systems. Then in the 90s, we moved from analog communication to digital communication. Towards the end of the 90s. We started having some texting, emailing capabilities. Then came the 3G era in the 2000s, where we start kind of moving online with our phones. And we start also benefiting from positioning capabilities thanks to the integration of GPS as part of our cell phones. We are now basically living the end of the 4G era, where basically we are enjoying in most of, let's say, urban environment that are well connected, high data rate connectivity with our mobile broadband, the smartphones. And now in 2020, we can say that as the 4G systems are kind of maturing, we are moving toward deployment of 5G, at least in few cities worldwide. So obviously, what you can notice from the chart I'm kind of showing in front of you, that it takes roughly 10 years to kind of develop a new generation of wireless communication system, another 10 years to kind of deploy it, use it extensively, make it mature, and then move on to the next generation. So as we are in the early 2020, or kind of 2020's kind of decade, obviously, as 5G is being deployed worldwide in few cities, obviously from research perspective, we are already starting essentially brainstorming about what 6G should be. And obviously, it is kind of a speculative period of time. There has been quite a bit of interesting perspective, vision papers, many workshops, summits, symposia, talking about the future 6G user cases, and so on and so forth. We had our share of that. We kind of published a paper early this year on what should the 6G be, that you can read at your own leisure in Nature Electronics. And obviously, 6G is going to be, like many of the previous generation communication systems, about pushing the envelope, going to faster data rate, new kind of user scenarios, lower latency, more capacity. But let us take maybe a moment and look at some other important trends and some important projection. Some of these trends are saying that, of course, the world population is increasing. Some other trends are saying that the world population is becoming more and more urban, and we are moving into more by 2050 into, if things keep progressing the way they have been progressing over the last decades, we are going to converge towards a more urban world, with 2/3 of world population living in urban environment and only 1/3 in rural environment. It's not clear that this is a nice kind of development, but that's how things are evolving. And because of that, obviously, we are to see more and more of these so-called mega cities with more than 10 million inhabitants. So with that, we can start also looking at the early deployment of 5G and some of the shortcomings of 5G. I mean, 5G is not perfect, at least in its initial deployment. And we start already observing some of the kind of, let's say shortcomings or blind spot of 5G. Of course, 5G has been the initial deployment quite successful in kind of pushing the envelope and increasing data rates, lowering latency, improving spectral efficiency in comparison to 4G. Nonetheless, one of the first kind of shortcoming, and let's see one of the kind of other coin of this mobile revolution, is that power consumption is increasing dramatically. So initial deployment in China, and China has been the leader in 5G, so most of the initial deployment and initial tests have been reported in some, let's say, Chinese authored paper. And they had this interesting white paper published in the 5th Global ICT Energy Efficiency Summit, and there was another paper in Nature Electronics also, mentioning that essentially power consumption for 5G in some bands is 3 times of 4G. And also we need we expect to see like more densification with 5G, which means it's expected to see 2 to 3 times more base station in order to achieve 4G kind of coverage with 5G deployment. So obviously, there is a strong concern, power consumption, and the concern is twofold. First of all, I mean, obviously, from a sustainability perspective, from a kind of a CO2 footprint, that's of course a concern. But the other also concern for all the mobile network operator is that the electricity bill is going to skyrocket, and that's obviously going at the end going to create a problem for the end customer, because the subscription, the money that they have to pay for their essentially cell phone is going to monthly cell phone subscription is going to go up. So that's concern number one. Concern number two, that in a way is led to this increase in power levels, is this kind of high level of concern among media, among public, about the level of EMF radiation and all the potential health risk associated with this extra RF emission from 5G base station. Actually, unfortunately, I mean, most of it, if not all of it, is really not kind of solid scientific information, and many of it actually is even, I would say, fake news linking 5G to coronavirus, as you have probably seen over the past spring, and this led to arson attacks in UK, in Ireland, in Australia, even recently actually in Austria. So it is people are taking that very seriously. But the matter and the fact is that RF waves, even millimeter wave, even I would say terahertz and visible light that are kind of being envisioned for 6G are really falling into the non-ionizing part of the RF of the spectrum, electromagnetic spectrum, which means that they really don't have enough power to break atoms or to affect our DNA. And as a result, I mean, there is no evidence whatsoever that this can lead to any kind of dangerous disease like cancers and cardiovascular kind of disease and so on. So far, all the evidence is not there for what basically the level of EMF radiation that the 4G or 5G network are emitting are of concern. But obviously, this doesn't mean that no more effort should be done. And I think effort should be done on two fronts. Obviously, from the biomedical, bioengineering front, we need to understand if actually there are other biological effects beyond the ionizing, non-ionizing effect, that can basically affect the human body, the health of people based on some EMF radiation, especially if we go towards millimeter wave and terahertz kind of emission in 5G and 6G. That's number one. And number two, I think as RF engineers or telecom engineers, we do need to do maybe some extra special efforts to try to design what some people are calling EMF-aware networks. Networks that try to maintain a certain level quality of service, but try to basically minimize the EMF radiation. And I will show you an example later on as we move on in this talk. The third concern of 5G is this concern related to global or like basically global connectivity, or the other way to get the connectivity or digital divide. So we tend to forget that about half of our population, a number between 3 billion to 4 billions, are either unconnected or underconnected, and basically they are not enjoying the benefits that come with connectivity. They are not enjoying all the, let's say, opportunities that come with connectivity. And the 5G, in a way, is more of targeting an urban environment and not really a rural, remote region, low-income neighborhood environment, and is in a way accentuating this digital divide. Actually, what we can say is that the COVID-19 kind of pandemic showed that connectivity can be a matter of life or death for people to access health information, health services. And the fact that we are creating this divide is not really helping at all. And that's another, in my view, important concern that hopefully 6G should address. So one way to kind of look at that is looking at this kind of sustainable development goals. So these are noble goals that have been adopted by the United Nations, a few years ago. They are about, creating a better environment in general for humanity, with more equality, with quality education, better health service to all people in this world, fighting poverty, improving equality among people, and so on and so forth. So these are really, again, very nice, noble goals. The initial kind of objective is to try to achieve them somehow by 2030, which is nice because it's kind of from a timing perspective, because 2030 is incidentally the year in which obviously probably the first generation of 6G systems, or the first, let's say, version of 6G systems will be deployed. So there is this nice timing between the, let's say, 6G deployment and the SDGs, as they're called in short, are going to be hopefully achieved or start being implemented worldwide. So this led to that many of us in this community of researchers in wireless communication feel that maybe contrary to all previous generation of wireless communication systems that have been essentially driven by profit, by financial consideration, the hope is that the SDGs are going to drive, at least in part, the evolution of 6G, which means that 6G should be, of course, like pushing the envelope like every single other generation of wireless communication system. But 6G should also be more digitally inclusive, should basically make sure that it's more sustainable, it contribute in a better way to like reduce the CO2 footprint, doesn't have any bad effect. We have to make sure that there is no environment and human health kind of bad effects. Of course, 6G should be secure because we'll be relying more and more in our daily life on wireless communication-based transaction, and as such, we have to make sure that 6G is super secure. And as we rely again more and more in our daily life on wireless communication networks, we cannot leave or the impact of a down like the outage of a cellular network or network or telecom network in general can have disastrous impact. It's like when you have a blackout in some areas in the world, it has a very serious kind of application. Same. So we need this network to become even more resilient, more robust, and more dependable. So in a nutshell, if you look at this classic, let's say, radar map showing the three famous user scenario of 5G, enhanced mobile broadband, which is about extreme data rate for like very hungry application from a data rate perspective, massive machine type communication, where basically here the aspect, the extreme aspect is about the number of device or connect device per coverage area. People are talking or targeting for 5G, let's say 1 connect device per meter square or 1 million device per kilometer square. 6G may be, like let's say 10-fold or 100-fold more density of connect device per kilometer square. And then ultra reliable and low latency communication. And here the extreme aspect is about lowering the latency as much as possible with a target of 1 millisecond for round trip for 5G, maybe even lower for 6G. So this will be again pursued as part of 6G. Maybe we'll see a combination of these use scenario being merged. Some application in gaming, in augmented reality, virtual reality may require essentially that you have to kind of have wireless communication links that have both enhanced mobile broadband capabilities combined with ultra reliable and low latency communication. So 6G can be about combining this user scenario, but on the top of all this, 6G should be also about adding an extra basic internet access use scenario, what is known also in some other circles as global access to the internet for all. This kind of vision that every single person in the world should have, let's call it a 4G like quality, from a quality of service perspective, connection in a 6G world. So wherever you go in rural, remote areas, low income neighborhood, you should be able to offer any person a 4G like connection that will allow the person to connect via voice, to connect, to browse internet, to basically video, audio, and even video stream at an acceptable quality. And that's kind of one, or what this can be viewed as one of the objectives of 6G. So let's look at some 6G technology trends. So obviously, when we talk about wireless communication, we have always to remember that one of the main aspects that we need to kind of factor or put into perspective is the spectrum. The spectrum is a limited resource. It's regulated everywhere in the world. It's optimized by the government in view of the different competing applications, starting from radio and TV broadcasting, all the way to military and governmental kind of agencies. And then the rest of it, of course, is kind of used for commercial services, for voice data streaming, and so on. Now, the spectrum is getting congested, and every single generation of systems is trying to optimize in the best possible way the use of the spectrum. So one very easy way to look at that is obviously to look at the area traffic capacity. That's the bit per second per meter square. You can divide this metric into 3 submetrics by multiplying up and down by node and by hertz. So you get the first factor, bit per second per hertz per node in red. That's essentially the number of bits you are able to squeeze in within this highway of information connecting your device to the closest access point, and that's called the spectral efficiency. Then node per meter square in blue, that's the network density. That's the number of access point that you can, let's say, kind of deploy within your coverage area, and the more you put, the more you densify your network, the higher is your network density. And then, of course, in green, we have hertz or the spectrum. So obviously, if you want to go from the current world where we have like this current small ball of performance to this kind of 1,000 better expected performance within 10 years, obviously you need to evolve, or you need to progress along these 3 dimensions of spectral efficiency, network density, and more spectrum. And that tells you the kind of some of the, let's say, emerging technologies that are being pursued, and some of them are actually have been there for many years already, or for many decades. They are just being improved. They are pushed to their limit, like MIMO. So like MIMO started like 2 decades ago. In 5G, people are talking about massive MIMO. For 6G, people are talking about ultra massive MIMO, where basically we are putting more and more antennas within limited space and going, of course, to higher frequencies, and this can go together very nicely. So basically, you see here kind of a description of a variety of interesting technologies. Obviously, we don't have here the time to go to every single one of them. So let me highlight few of these technologies and show how they can actually improve or help us improve the performance of 6G systems or beyond 5G or 6G systems. So the first one I would like to highlight is smart radio spaces, known also as artificial radio space. The idea here is basically, in a way, it's kind of a natural progression or evolution within the area of communication theory. When we started looking at communication theory in the 40s of the previous century, obviously the first effort was trying to optimize the receiver with the work of Shannon and also the match filter and all this kind of classical work that has been done in optimization of communication systems. Then sometime in the 90s, we start talking about optimizing the transmitter, assuming a certain feedback between receiver and transmitter. And we are now living in this world where basically we optimize receiver and transmitter or transceiver optimization to get the best out of our communication link. So the natural evolution is actually, what about if we also start optimizing, let's say, the channel, the medium that connects the transmitter and the receiver. In other words, trying to create an artificial or a smart radio space in between transmitter and receiver in order to improve our end-to-end quality of service. This can be achieved by using these metamaterial surfaces or these tunable reflected array consisting of low cost, low power, low, like passive in a way, active reflecting elements that can direct energy in areas where basically you have obstruction or not spots. So you are trying to make the propagation channel more favorable in order to satisfy your end-to-end quality of service. And these kind of reflecting surface can be kind of put on the walls in indoor environments or in the painted, like let's say, in the facade or on the top of facade of buildings in some neighborhood. So this is a kind of an illustration of how you can use these reconfigurable intelligent surfaces. You have here like a user trying to connect to a base station. There is a blockage in between. The quality of the link is bad, so he's not enjoying a very good SNR. And what happened here, you can rely on this controllable reflection coefficient that is, kind of controlled in this surface on the, like basically kind of that's covering this building to create a virtual, if you will, or a non-direct line of sight between the base station and the user and end up having a much better SNR condition and much better link condition. You can actually also use the same kind of reflecting surface to improve the interference condition. So you have here two users, each one connected to its own base station, the closed base station, but because of the kind of the fact that one of the base stations is close to one of this user, you are also interfering, or there is interference coming from this base station to the user. But because the base station knows exactly the kind of signal it's transmitting, it can also send, the same signal through this reflecting surface and with some kind of good adjustment of the phase, you can essentially cancel the interference at the mobile user through this kind of reflected signal and improve the SINR of the second user through this reflecting surface. So obviously there are a lot of potential advantages that come with this reconfigurable intelligent surface. You can essentially kind of eliminate node spot, as I'll show you. You can minimize interference. You can even create some physical layer security, because at the end of the day, you can decide that you want the particular environment to not leak any information, and you can make essentially all the walls absorbing all the incoming wave without any reflection, and you can create super secure kind of environment that way. So let us kind of illustrate that through this elaborative example. So you have here a particular coverage area. You have a base station in the middle of this area. This base station is trying to connect to a variety of points within this coverage area. And in green are the points without obstruction, enjoying very good SNR. In red are not spots, which are basically areas that are kind of obstructed by some buildings. In blue here, these buildings are between the base station and these not spots, which means that these red spots are essentially experiencing bad SNR or are essentially not what we would call not spots. Now, what happens if you kind of pick this building, for example, and choose to put a reflecting surface that can basically defy Snell law and reflect, incoming signal in all kind of ways, not necessarily like having the reflecting, let's say, angle equal to the incident angle, because we can do all kind of things of this kind with meta surfaces. So this is what you end up having. You end up having reflection on all kind of interesting direction. And in other words, you can replace many of these red not spots into green, basically well covered spot. In other words, you move from this kind of coverage before kind of using this smart wall, if you will, or this kind of smart surface into this kind of coverage with much more green, where essentially a lot of these not spots have been eliminated. So one study we did over the last few months, and it's led to a paper that appeared in the recent JSAC, basically is trying to quantify statistically how much, let's say, reflecting surface should be used within a certain coverage area in order to minimize or even kind of at some point completely remove basically these not spots. So again, this study could have been done using an optimization framework or a stochastic framework or stochastic geometry framework. We went for a stochastic geometry framework, and we assume that we have a certain coverage area where users are randomly distributed, and you have a base station. So it's kilometer by kilometer. We have about, it's like, we assume it's like a highly urban, densely populated area with 500 buildings per kilometer square. We assume that we have 10 base stations per kilometer square deployed within this coverage area. And because of the, high level of building density, you have a lot of obstruction, and this lead to all of these not spot in red. And then we start like randomly picking some of these buildings and transform them into buildings that are equipped with reflecting surfaces and try to see how many of these not spots can be eliminated accordingly. So here we starting point 0% reflecting surface. Now we move to 5% reflecting surface, and already you notice quite a bit of reduction in terms of not spots that are in red. We have now only few of them. Then you go to 10%. By the time you reach 10%, you have only 4 not spots. And then eventually, if you reach 40%, which means if basically 4 out of 10 buildings are equipped with this reflecting surface, then obviously what we see here is that we eliminate all not spots. And this happens without having to basically add any extra power. We are still using the same number of base stations, but we are using all of these reflecting surfaces to transfer power in a desired way in area that basically have been blocking all of these, let's say, have been blocked by building previously. So that's the beauty of this framework. So if you will, if you want to quantify that, this is a coverage probability as function of the average power consumption per unit area in watt per kilometer square. As a benchmark, we start with that once we have no, if we have no reflecting surface. And then as we keep increasing the reflecting surface from 10%, 20%, 60%, 100%, then obviously coverage probability increase without coming at the expense of an increase in your average power consumption per unit area. Let me now talk about how we can address the second concern is by trying to go into more and more of this so-called EMF-aware cellular network design. And the way we do that, at least there are many ways of doing that, but what we are proposing is to use UAV-assisted communication, as you know, even as part of 5G research, people have been advocating for the usage of drones or UAV for emergency communication, to offload in massive events, to bring global connectivity through these high altitude platforms. Of course, you can use always UAV and drone in military scenarios. And the idea is that one of the nice things about UAVs is that they can provide better line of sight condition with ground user. As you know, the higher you go in altitude, the higher is probability to increase your line of sight, and with a better line of sight condition, you can create better end-to-end SNR, and that's one of the interesting kind of things that you can get with UAVs. And of course, UAV, they can follow the traffic, and they can always position themselves in the center of any hotspots. And the fact that they can track the time varying traffic demand, spatial distribution, can create always better channel condition for communication purposes. So that's what basically led people interest in UAV. Now, most of the work has been focusing on what we call here in this presentation untethered UAV. These are like the well-known standard free-flying UAVs. But these untethered UAV have some limitation. One of their limitations is that essentially they suffer from a limited battery capacity. And this limited battery capacity limit their basically flight time and limits their basically payload. And when we say they limit their payload, which means that we cannot do sophisticated MIMO, we cannot have enough antenna, enough RF chains. So, you know, you may end up having some very basic capabilities in these UAVs, and for a short period of time. On the top of that, you have to remember that UAV at the end of the day is just like a relay. So it needs a backhaul or feeder link to a gateway on the ground. And this, comes at the expense of some extra resources, and it's not always reliable. And then the third thing is let's say, we can suffer also from the so-called drone flyaway risk or problem. In other words, because of the fact that these drones again are controlled remotely wirelessly, at some point you can lose control of these drones, and they can crash, or they can become like a problem if you kind of lose them. And that's why there has been also an interest, at least from our side, and we had a couple of papers on that, on looking at what people call tethered drones. These are drones that are equipped with a cable that connects the drone to a ground station. And this tether basically provides the drone with two things. Number one, power supply, which makes them fly for hours, if not days. And then also you can insert within this tether a fiber optic, which means you create this feeder link between the tethered drone and the flying tethered drone and the ground station, and you don't have to rely on a wireless backhaul feeder link. And of course, because it's attached, you don't have to deal with this so-called drone flyaway risk or problem. So in this context, you start using this tethered UAV that can basically kind of be connected to this ground station on the top of a high altitude, rise building in downtown. You can use them also in rural environment, and you can use them for offloading the same way you would use an untethered drone, but with the extra capabilities I just mentioned. So obviously, if you try to compare an untethered drone to a tethered drone will give you a better endurance, more payload, better backhauling capacity. But on the other hand, it will make you lose a little bit in line of sight probability and mobility and relocation flexibility, because you're not completely free to fly anywhere you want because of the tether constraint. Nonetheless, it can be viewed as a good trade-off between basically a terrestrial base station with all the limitations that come with terrestrial base station, because it's low altitude and that cannot provide always the best line of sight condition, and a free-flying tethered drone, free-flying untethered drone. So in this context, we try to use these tethered drones to basically create or design an EMF-aware cellular network. And the main motivation behind the work is that, contrary to what people think, most of the EMF exposure is not really coming from downlink, it's not coming from base stations. In other words, users are typically far away from base station, and the amount of EMF exposure, or amount of RF power you get from the downlink onto the faraway base station is minimal. Most of the EMF exposure is coming actually from your own phone or from your own tablet or from your own laptop, especially if this laptop or phone is far away from the base station. In other words, when your uplink is operating at low SNR and you have to use maximum power from your cell phone or from your tablet to connect to that faraway base station, this is where you have most of your EMF exposure. So the idea we came up with is, what about we decouple uplink and downlink? And this concept of decoupling has been used in a different other context to improve energy efficiency, to improve some other kind of performance metrics. In our case, we would like to kind of minimize EMF radiation, and our idea is to use base station for downlink and to use these tethered drones that are connected to nearby buildings that are around the user clusters. And we use what we call green tether UAVs, which means tether UAV that will be just listening, that will be just receiving information and essentially backhauling that information to the backbone, to the network backbone. So these tether UAV, they'll place themselves in the best possible position to create the best possible channel with the users, so that user will transmit at minimal amount of power, and the signal coming from this will be received by this tether UAV and backhauled. On the other hand, the downlink can come from the base station. So the idea was to design this network by kind of trying to do association, where first of all we should kind of place this tethered drone within a certain coverage area. Once you place them, which user should be connected to which tethered drones. Yes. So to make a long story short, obviously it's a complex optimization problems, but we were able to solve it using different kind of heuristic approach. And as a benchmark here, we showed the kind of average exposure index, that's a reflection of the EMF exposure as function of the number of UAVs. Now, obviously, if you don't use this approach, use the base stations like uplink, downlink as usual, you end up with this very bad exposure on the top, is the flat kind of line. And then as you start using this green antenna or green UAV concept, if it's just antenna, which means you don't use UAV, you don't go to good altitude to create the best possible channel, you get improvement, but not as much as you want. But then as you optimize with this kind of shrink and realign algorithm or the K-means algorithm, you end up getting the best kind of average exposure that are illustrated in this curve here. And you are getting basically reduction between 30 to 50% compared to random and worst location placed green antennas if you use optimized tethered UAV kind of deployment. Now let me try to address in the remaining time. How much time I still have, please?
Yes.
Professor Das, so how much time I still have?
Another 20 minutes you can carry, Max.
Great. I think I have enough time to go over all my slides. So essentially, the third concern is how we can connect this so-called base of the pyramid. And base of the pyramid, by the way, is not really my own invention, or it's not my own word, let's say. It has been kind of introduced about 20 years ago by these two famous economists, Prahal and Huart. And the idea is actually you should not see, bottom line, that connecting this like the base of the pyramid, these are the people who are earning the least amount of money worldwide, and that creates the highest number of people worldwide, and that these are the people that tend to be unconnected. Connecting them should not be viewed basically as a humanitarian or as a charity, rather actually as a way to empower this base of the pyramid and to create this huge market of creative and resilient consumer and producers that have been currently essentially excluded from formal markets. And giving them access to this market, essentially you can create a lot of economic growth. And in a way, this explains why many of these GAFA of the world, like the Google and Facebook of the world, are really after this connecting of the base of the pyramid. And a lot of the interesting research being done these days essentially in the area of global connectivity is done in the connectivity lab of Facebook and Google and so on. So if you look at the map of global connectivity, obviously it doesn't look good. Many of the countries are still in this kind of living in this digital darkness. And the reason are many. I mean, beyond like literacy. I mean, I'm here, I'm talking here computer literacy, or sometimes actually content where people don't find the relevant content in some villages or rural areas. But actually, some of the reasons are economic, as you know. Mobile network operators tend to deploy their, let's say, equipment in densely populated areas so that they can get back money. They use a kind of a return on investment kind of model, and it doesn't make much business sense for them to lay 100 kilometer, if not 1,000 kilometer of fiber optics to reach, very sparsely populated, remote, rural regions. So this is kind of some of the reasons that kind of lead to these bad statistics. On the top of that, as you can imagine, if you don't have a power grid in this remote location, obviously you cannot have a reliable telecom network, because telecom network requires a reliable power grid to be up and running. So, anyway, all these reasons are there, and this leads to this digital divide that basically doesn't touch only rural area. It does touch also low-income neighborhood, temporary kind of communities like refugee camps. So bottom line, every time you have a kind of a low average revenue per user or low average revenue per area, obviously there is no appetite for these or willingness for this mobile network operator to kind of serve these users in a cheap or an affordable fashion. And this leads to this connectivity divide that we are observing in low-income neighborhood or in remote rural areas. And the idea is that hopefully 6G will help bridge this connectivity divide, help kind of essentially go against this vicious cycle of digital divide by bringing connectivity to many of these remote areas. And one question that we would like, or one objective that we want to go towards, is to go beyond this, let's say, we can say narrow concept of smart city to the broader concept of a smart village, smart hamlet, smart living. If you connect these remote areas, maybe you can trigger a counter-urbanization process, and you don't have to have all these people living in congested, polluted, kind of cities, but rather can offer prosperity, can offer economic development, can offer economic opportunities to people working in a less crowded environment and basically having or benefiting from good education service, health are provided by a more dense environment. So that's kind of the concept that we are kind of advocating for, and that we hope that 6G is going to help achieve in the coming 10 years. So one may argue why it again took us so long to start thinking or to try to develop all the technology that make kind of global connectivity affordable. And the reason can be summarized in this diagram that you see in front of you. This diagram shows the quality of experience in terms of data rate and low latency as function of the cost per user in remote low population density areas. And what you can see here, that obviously geostationary satellite, these are the classic geostationary satellite, which are great for TV broadcasting. I mean, essentially, from a quality of experience, they will not give you the quality of experience you need from internet broadband connectivity. Now, if you want good quality of experience, you need optical fibers, you may need microwave links, but they are very expensive to deploy in sparse populated area. So if you want to go after the so-called global connectivity holy grail, on the left, on the top left in this diagram, you need to find some other solutions in order to achieve this kind of nice prophetic, let's say, statement or vision made by or prediction made by Nikola Tesla about 100 years ago. So now one way to achieve that is to go or to adopt integrated space, air, ground networks. In other words, try to kind of rely on these backhaul and access solutions that are coming from the air. This is how we achieve larger area coverage by relying on satellites, on low altitude platforms, on high altitude platforms. This is the way to achieve better global connectivity. You cannot rely on just the terrestrial infrastructure. It's very costly. It doesn't scale. But if you go in altitude, you start creating a base station with a much bigger footprint, you are able to create an economically viable network that can start serving this remote area in a again economically viable fashion. So from a backhaul perspective, you would like to rely on this variety of satellite communication technologies. So there is always this trade-off between latency and altitude. So the higher you go, the bigger is your footprint, but the higher is your latency. The lower you go in altitude, the lower is your footprint, and the more you have to have more and more satellites, because satellites are not fixed with respect to the ground. So you need to have like a constellation of satellite, but the lower is your latency. And there are a lot of interesting projects ongoing in the direction of very high throughput geostationary satellite and the direction of like low cost, essentially LEO satellites, as you may have heard about many of these projects launched by Telesat, by SpaceX Starlink or by Amazon Kuiper, start targeting, and I will not say even 100, but actually thousands of satellites to create this backhaul solution. We have been actually working more on the very high throughput satellite, which are geostationary satellites that basically have two sides. One side, which is the RF side, basically providing like shapeable RF beam that can follow the traffic on the ground. These are the yellow beam that you see on the slide. And from the other side, we have kind of feeder link that we can see easily 10 years from now moving towards free space optics as Ka band start being completely used for the user link. So free space optics can be a very good solution to kind of address the spectrum shortage, and obviously with it comes many challenges that I will talk about quickly. Some of the challenges about alignment between satellite and the optical gate station on the ground. The other challenge about weather condition, you can have blockages in terms of clouds, and as such you may need to rely on multiple optical gateway stations to create site diversity. So here I'll go very quickly through that. I mean, I will just cite the paper. We have been looking at the advanced multiple detector array kind of techniques to improve the positioning, acquisition, and tracking for FSO links. The idea is to use, instead of a single detector, multiple detector, and with that we show that we can improve quite a bit the positioning, acquisition, and tracking of many of these systems. So I will skip that, and then the slides, I'll make them available so you can look at them, and if you want to know more about this technical aspect. Now, of course, beyond backhaul, you need access. Now, classical ways to deploy or to provide access in remote areas is to rely on these masts or use TV towers on the top of hills, let's say, and you can create this macro cell of tens of kilometers. You can use beachfront, let's say, spectrum, sometime in a TV white space fashion. So basically, user can connect to these TV towers, and that's how they can get their internet signals. Now, may happen that the TV tower are not there. We don't, or we have flat terrain, and there has been kind of interest in creating these again aerial solution through tether UAV or tether balloons. So tether UAV can give you a cover of say the 30 to 40 kilometers radius, whereas if you go to this tether balloon at an altitude of 500 meters all the way to 1 kilometer, you can create macro cell with a, let's say, a coverage of 100 kilometer radius. So that's really, like a huge macro cell, and that's economically cheaper than just building a super tower, or it's like a super tower. It's more, it's is equivalent to multiple towers on the ground. You can even go to higher altitude and start beaming internet from the stratosphere. At 20 kilometer altitude, you can have like a bigger footprint, and you don't need a tether. There are multiple projects like led by Google Loon, or maybe the Zephyr Airbus project, or Stratobus by Thales. All of them are advocating for using of high altitude platform at 20 kilometer, and then you can have multiple of these platforms to kind of create a stratospheric, let's say, cellular network that can cover these remote areas, with obviously at least one or a few of them acting as a mother, let's say, drone or mother hard platform to connect to the internet or the backbone internet on the ground. Now, one other solution that is actually quite nice or applicable, let's say, to low-income neighborhood is to rely on the so-called integrated backhaul access. These are wireless mesh networks. You can have point of presence of the internet at the boundary of a certain like low-income neighborhood. You don't want to use the classical cellular deployment that can be expensive because you have to rely on spectrum that can be like the auction spectrum that can be very expensive. So if you want to use unlicensed spectrum, very short range, you can create this again mesh network where basically every node here is acting as an access point with Wi-Fi, let's say, or 5G or 6G eventually, and also is acting as relay, so as a router. So essentially, you create this mesh network, and it can be like this relay can be on the top of every second, let's say, lamppost, and you have this kind of hotspot around this lamppost. And if you are in that neighborhood, you connect to that particular lamppost Wi-Fi point to connect to the internet, and the information propagate within that kind of network. So that's another way of creating access in a for low-income neighborhood in an economically viable fashion. Eventually, this can lead to this emerging concept of network in a box, known also as pop-up network, because as you know, I mean, if you invest in connectivity for remote areas, at the end of the day, you are also investing in connectivity for emergency communication, because yes, most of us live in kind of urban environment that are well connected, but we tend to forget that at any point, because of natural disaster or man-made catastrophe, we can lose connectivity because the ground infrastructure can be destroyed, and you need in that case to get internet from the sky. And that's what happened actually in 2017 with the Maria hurricane that hit Puerto Rico. It was thanks to the Loon project that basically internet was provided to this Puerto Rico island. So this self-organizing pop-up network or network in the box are there to basically provide internet in the case of disaster, offloading in the case of event that needs extra capacity for a short period of time. They can be very helpful if you are sending basically scientists in the Antarctica or the Amazon, and they want to connect and start video streaming in real time in the middle of nowhere. Of course, they are very helpful also for moving cells like airplane, ships in the middle of the ocean, trains, or military missions in the middle of kind of non-urban environment. So this network in the box or pop-up network are essentially a generalization of this problem that we have been talking about. And whenever you talk about network, you talk about backhaul solution, satellites in particular, spectrum access or access solution through kind of these drones or balloons, and basically you need to think about power supply. It's very important to make sure that they have enough power supply in the form of maybe energy harvesting, and they have to be fastly deployed in the middle of rural or remote areas. I have been talking mostly about connecting people, but actually once you create this global connectivity environment, you can start connecting all kinds of devices and sensors, and this can help for a variety of other interesting applications related to the United Nations SDGs, like smart farming, that can help reduce the cost of food and improve the efficiency of agriculture. It can help us, connect all kind of device or sensor in a variety of environment and start monitoring in a better way and in real time climate and weather worldwide. So with that, I would like to thank you for your attention. And as telecom engineers, obviously, we would like always to go to the next level. And we hope that with the deployment of 6G, we'll be able to achieve this kind of vision that Tesla put forward like 100 years ago. And I hope that 6G will be indeed the time where we'll move into this global connectivity environment. Thanks for your attention. I'll be happy, of course, to take some questions.
Thank you, sir. Now the platform is open for questions and answer from Professor Mohammed's side. Participants, please start asking.
Thank you, Professor Mohammed. This is Dr. Uday here. Hello.
Yes, I hear you.
Yeah, can you hear me? Yes. So
yes,
it's a very wonderful talk. Actually, my thesis is related to femtocells where interference mitigation. We developed algorithms using game theory. What about the scope of this extending for the small cell networks? What about this research happening in the area of interference mitigation for the small cell networks? Could you please elaborate on it?
Yeah, I mean, of course, interference is always a very hot topic. As you densify your network, you create more interference. I have been talking about this large intelligent surface. Of course, as a starting point, at least from my perspective, we looked at scenario where interference has been neglected. But obviously, as you create more reflection, we are creating also interference. So any ways or methods that are there to kind of reduce interference or mitigate interference or use interference for energy harvesting. As you know, interference can be used sometimes as a way to kind of generate energy using sweep energy harvesting. Is a good topic, and it will be still alive, and there will be still a lot of interesting research done as part of 6G in the form in this area of interference mitigation or interference cancellation.
Yes, because one of the challenging tasks is once you densify this, there is a limit where this data rate may not increase. That I mean to say that capacity, overall capacity may not increase. That's what I have studied very long back in some paper. What's your opinion on that?
Yeah, I mean, there is, of course, there is limit, but maybe we should densify in a smart way, and that's why having this extra dimension, the aerial dimension, like with UAVs, can create better channels. So you, with the same level of density, but with the right altitude, with the right kind of probability of higher line of sight, you can create more capacity, let's say.
Okay. Thank you so much, Professor.
Thank you.
Dear Professor Mohammed, this is Vishnu.
Yes.
Sir, I have a query about reconfigurable intelligent surfaces.
Okay.
Sir, I have learned that the surface area of this reconfigurable intelligent surface should be very high to work efficiently. And as we are steering the beams in a particular direction, we need some SDR setup to do this. So how the cost incurred will the cost incurred will be high or less when compared to the massive MIMO systems?
Yeah, of course, the cost, I mean, as you know, when we start doing research, we start looking at the potential, we start to benchmark and say how much we can achieve with these new technologies. And then we start looking, once we see the potential, we start benchmarking, we see the kind of gains we can achieve. Then we can look at the cost aspect. Like now, for example, people are realizing that, yes, massive MIMO can bring you these kind of very nice data rates, but is it economically viable? Maybe it is in high, dense urban environment when you can serve all these users who will pay subscription, but it doesn't make any sense if you go to lighter deployment or rural areas. So again, so that's I'm trying to give you by analogy or trying to answer by analogy your question by saying that as a researcher we start to get potential of a technique, but then when we see that indeed it's interesting or it's kind of promising, we need, of course, to start looking at how to make it lower complexity, how to make it like basically lower cost. But for now, we are at the early stage of research, at least from my perspective, on this intelligence reflecting surface. We are looking still at the potential. We did not look at how much they will cost and how practical they are from deployment, from a cost-effective perspective, you know. But definitely, this is at the end what make a technology fly or just remain as a paper, you know.
Yes, sir. Yes, sir. So one more doubt. Is the spectral efficiency achieved using these intelligent surfaces will be higher than massive MIMO networks?
In a way, it's a distributed. The way I see it is like a distributed MIMO system, so you can start achieving similar results, but also without having to have a line of sight. So in other words, like essentially, you are able to increase an average all your spectral efficiency, even in an area where essentially you have obstructions, or you used to have obstruction because you don't have a good line of sight condition.
Yes, yes. Thank you, sir.
Hello.
Yes.
Hello. Good evening, sir. My name is Dr. Suman Kumar De. So I have a question that when you talk about the satellite that of free space optics. So my question is that, so when we go for the 6G, so in that case, can we use the other optical, means wireless optical communication technology, like that your visual light communication or light fidelity or optical camera communication, like that kind of wireless communication technology?
Yeah, I mean, I think optical wireless communication have different aspects. Like you mentioned, there is like camera communication, there is visible light communication, there is free optics. Every single one, it's a niche area. They are not all used in the same kind of environment. When you talk about satellite communication using optical wireless, we are talking about this backhaul or this feeder link, point to point. So this is either between satellites or between a satellite and a ground station on the ground. And in that case, we use free space optics, laser, free space, super high data rate. Now, if you are talking about like indoor environment where you want to kind of address the spectrum scarcity issues and go beyond Wi-Fi, then you start talking about Li-Fi or visible light communication. If you are talking about maybe RFID-like kind of situations or maybe vehicular networks, you can use optical camera communication. So I mean, optical wireless communication is a large field by itself with many niche, and every niche has its own technology, right? I mean, it's not like the same, like you don't use FSO everywhere or visible light everywhere. Everyone has its own interesting niche. But for satellite, I think what is being advocated for is free space optics in the near infrared.
Okay, thank you, sir.
I see a couple of questions in the chat box.
Okay.
Can you see, Professor Mohammed?
Massive MIMO utilize higher order antenna, the transmitter. What about the antenna spacing between the elements? How about the power consumption of the antennas? Yeah, I mean, of course, I mean, like massive MIMO, people are talking even about ultra-massive MIMO, and they are all about increased number of antenna. And with it comes power consumption that I mentioned. This is one of the shortcomings of 5G. Yes, you can get this record spectral efficiency, you can get this record data rates, but you are not energy efficient. And that's what has been observed in the first deployment. And now we have to come up with a trade-off. We cannot just leave with this kind of we need to do a better job at being more energy efficient, be more kind of aware of the amount of power that needs to be used, and of course the radiation effects. So it's a trade-off. Technically speaking, yes, we have been quite successful in kind of making massive MIMO, and people are talking, as I told you, about ultra-massive MIMO. But I think we should look at the other face of the coin, let's say, and not look at only spectral efficiency and record data rates. We should have to start looking at energy aspect or power aspect.
Sir, I have a question.
Go ahead.
What is the major difference between reconfigurable intelligent surface and relaying? Both are used for coverage extension in non-line of sight environment, maintaining the reserve signal strength. Yeah.
A very good point. Sorry, maybe I wasn't very clear on that. I mean, the main difference is that relay typically are active. It's like either amplify and forward, they call them forward, which means they come at the expense of extra power of the relay. Reflecting surface to a certain extent that they are meant to be fully passive. I mean, of course, there's nothing that is fully passive. Probably you need some little bit of power to control things, and but at the end of the day, they don't regenerate signal. There is no noise injection. It's just reflection. It's like a mirror, kind of, you know, like as an image. So basically, they are relays, but they are passive relays.
Yes.
So that's the difference between reflecting surface.
So it's a transmit power saving we are doing.
Yeah, that's what I'm trying to say. So we are trying to transmit power or try to achieve, create like relaying or no virtual line of sight at no extra power.
Yeah. Any more questions from participant side, please?
Hello, sir.
Yes.
Hello, sir. I am Gyanaranjan Mati. Hello.
Yes, I hear you.
Yes, sir. Sir, can we use RFID as an intelligent reflecting surface, because it has also means passive means that intelligent reflecting surface don't have any transmitter module, and RFID is having don't have that transmitter module also. Can you use RFID as a intelligent reflecting surfaces?
Yeah, I mean, there is some interesting kind of now people, obviously it has been an active area for the last 2 months, and there's tons of paper being published now on reflecting surface. And this idea of combining what you may call reflecting surface with backscatter communication, if you want to call it RFID backscatter communication, there are people who already are thinking about that along these lines. I have not been very active in this area of combining reflecting surface backscatter communication, but definitely it's in a way it's these are two areas that can come very nicely together. So you can not only reflect, but you can reflect, and on the top of that maybe inject some bits and act as like RFID or backscatter communication. So yes, that idea is there too.
Thank you, sir.
I don't see more questions here.
Hello, sir.
Yeah, another question. Okay, please ask.
Sir, I have a query. Can cognitive radio-based IoT or communication be used to reduce the digital divide in rural areas and for emergency connectivity? Because we were talking about this digital divide and emergency communication. So I have a query, sir.
Definitely something of course I didn't talk about. As you know, or as you may know, part of this reason behind this digital divide or cognitive divide is some like outdated regulations or like outdated policies that make the spectrum kind of be kind of property of MNOs, which means that actually you can be in an area where actually there is no good coverage, but still you cannot use a spectrum because it's owned by a company that doesn't see the point of deploying equipment there, although they maybe are supposed to do it, but they will do just lip service and offer very bad connectivity to these people who are in the remote areas or the fringe of their coverage area. So in that case, if you can start using spectrum sharing, you can use TV, for example. White space has been used quite a bit to kind of basically cover these uncovered or underserved areas. So definitely, if you want to bypass some regulation, I mean, unless you change, either you change regulation and there is this movement to make operator kind of have different kind of flavors. Some operator may be operating in rural environment, are different operator in urban environment, or like like trying to solve that problem that way, or using like spectrum sharing or TV white space techniques to be able to use a spectrum in a clean and an efficient way in rural remote areas.
Thank you, sir.
Thank you very much, Professor Mohammed. You have really exposed us to the benefits of upcoming 6G. We came to know about the smart radio configuration with the reconfigurable intelligent surface, interference cancellation with destructive combining out for improving the SINR. Then also we came to know about the UAV assisted communication and very interesting green tethered UAVs for EMF aware cellular network. Also we came to know about the integrated space air ground network for better perspectives and the backhauls, satellite constellation backhaul. We are now dreaming of smart city, smart living and smart environment everywhere, and society at large will be highly benefited by the perspectives and applications of 6G. So hope all our participants have several new innovative thinking about the research to be carried in this 6G. And hope this lecture will highly benefit them to critically think about about the upcoming 6G to be addressed. Thank you, Professor Mohammed. Thank you a lot for accepting our invitation. It's a great opportunity and pleasure for my part to interact with you in this forum. Thank you, sir.
Thank you very much, Professor Das. It's really an excellent summary. I think you summarized all in 3 minutes. But I appreciate your really kind of highlighting all the points. And it'll be always my pleasure to be part of these online forums so that we exchange ideas and we kind of learn from each other. Thank you very much.
Sir, the National Institute of Technology Rourkela community is highly appreciates your presence in this platform. Thank you, sir.
Thank you. Thank you very much. Bye.
Bye.